Hi everyone, welcome to Go Classes. So in the last lecture, we were discussing planar graph. We have already seen what is a planar graph, what is Euler formula for planar graph. The proof of Euler formula also we have seen. Now in this session, we are going to discuss some important results. Okay. So in planar graph, for planar graphs, some important results are there. Those we will discuss in this session. Okay. So let's start now. See, this we have already seen this point. This note we have already seen. If you remember, in any connected simple planar graph, if you have at least 3 vertices, then degree of every face will be at least 3. Yes or no? This we have already seen in our previous lectures. That if you have a connected planar graph, if you have a connected planar graph, if you have connected planar graph, okay, with how many vertices? With at least 3 vertices, with at least 3 vertices. So if you have a connected planar graph with at least 3 vertices, then what will happen? Then degree of every face will be at least 3. Okay. Then degree of every face, what that will be? Degree of every face that will be greater than equal to 3. That will be at least 3. Yes or no? If you remember, I told you degree of face can never be 1. This point you already know. Degree of face, okay, this is 1. This will never happen. Okay, this will never happen. So you can see degree of face equal to 1. This will never happen. This will never happen. Correct? If you remember, in the previous lectures we have already seen this, that degree of face will be 1. That will never happen. Okay, degree of face can never be 1. This will never happen. Also, I told you, in a connected graph, degree of face is equal to 2. Degree of face equal to 2. Okay, that will happen only in K2. That will happen only in K2. Okay, we are talking about connected graph. We are talking about connected graph. So degree of face will be 2. That will happen only in K2. So if you have at least 3 vertices, then degree of every face will be at least 3. So these points we have already seen in the previous lectures. This note we have already seen. So finally, this is important. So remember, if you have a connected planar graph, remember we are discussing connected graph here. If you have a connected planar graph with at least 3 vertices, then degree of every face will be at least 3. Okay, is this clear? So very simple point. Degree of every face will be at least 3. Now let's see our first result. See, this is our result number 1. Result number 1 is saying, in any connected simple graph, whatever connected simple graph you take with at least 3 vertices, then number of edges will be less than equal to 3v minus 6. Okay, this is the result. This is the result we need to prove. We need to prove this result. We need to prove that if you take any connected planar graph, you can take any connected planar graph with at least 3 vertices, then number of edges will be less than equal to 3v minus 6. This is what we need to prove. Okay, and the proof is quite simple. Let's see the proof. Let's see the proof. Given is connected planar graph. This is given to you that you have a connected planar graph. That you have a connected planar graph with at least 3 vertices. Okay, with at least 3 vertices. Number of vertices is at least 3. So this is what you have. If you have a connected planar graph with at least 3 vertices, then in this situation, degree of every face, what will be degree of any face? That will be greater than equal to 3. Yes or no? Very simple. Now, what are the total degree of faces? What is the total degree of faces? What is the total degree? Total degree of faces. Okay, so tell me, what will be the total degree of faces? That will be twice the number of edges. That will be twice the number of edges. Okay, now you can see. See, this is the minimum degree, right? Can I say this is the minimum? Okay, because degree of every face that is greater than equal to 3. So can I say that what will be minimum? See, this is minimum, right? Can I say this is minimum? This is minimum. So if I do this, if I take this 3 multiplied by number of faces, that will be less than equal to the actual value. Yes or no? Agree with me? See, this 3, this is the minimum. Degree of every face will be at least 3, will be greater than equal to 3. So if I take this minimum, means if I multiply this 3 with the number of faces, then that will be less than equal to the actual value. That will be less than equal to the actual value. Correct? This will be less than equal to the actual value. And this actual value, that is equal to 2e. So finally, I can say that you got 3f. What you got? You got 3f is less than equal to 2e. Okay, and what Euler theorem formula says? What Euler formula says? What Euler formula says? Euler formula says that for connected graph, okay, if you have a connected graph, we have a connected graph. So for connected graph, what Euler formula says? It says that v plus f, that is equal to e plus 2. Now here you can combine these two. Okay, from these two, what I can say? See, notice from here I can say f is less than equal to 2e divided by 3. This is what I can say. Okay, and from here I can also say, that v plus f is less than equal to v plus 2e divided by 3. Okay, and you can notice this v plus f, this is equal to e plus 2. This is equal to e plus 2. So finally what we got? So finally we got that e plus 2 is less than equal to v plus 2e divided by 3. Now you multiply with 3 and you solve it. Then what you will get? You will get e is less than equal to 3v minus 6. This is what you will get. This is your result number 1. Okay, that's it. So I hope you understood this. This is your result number 1. Please tell me, did you understand? See, the proof is quite simple. You already know that degree of every face, that will be at least 3. Yes or no? See, the proof. I am again repeating this. See, you have a connected planar graph. What is the total degree of faces? Tell me, what is the total degree of faces? What is the total degree of faces? If I find what is the total degree of faces, that will be twice the number of edges. That will be twice the number of edges, right? Okay. You tell me one thing. A simple question I am asking. See, this is your total degree of faces. This is the total degree of faces. If I write that this 3 multiplied by number of faces, can I say this will be, can I say what will be relationship between this and the total degree of faces? Can anyone tell me? What will be the relationship between this and total degree of faces? What will be that? Okay, see, very simple point. Okay, let's assume you have k faces. Assume k faces are there. Okay, see, very simple point I'm saying. So you have k faces like f1, f2, f3, and so on, fk. Okay, see, this will have some degree. Yes or no? This face will have some degree. This face will have some degree. For example, d1. This face will have some degree, d2. This will have degree, d3, and this will have degree, dk. Okay. Now, what the total degree? Tell me. If I add all of them, d1 plus d2 plus and so on, dk. If I add all of them, then what that will be? That will be twice the number of edges. Okay, total degree of faces. Total degree of faces, that will be twice the number of edges. Now you tell me, can you notice this d1 is greater than equal to 3? This d2 is greater than equal to 3. This d3 is greater than equal to 3. And this dk is greater than equal to 3. Yes or no? Degree of every face is at least 3. So I can say degree of this face is at least 3. Degree of this face is at least 3. Degree of this face at least 3. And degree of this face is also at least 3. Now, tell me one thing. If I take minimum, like if I take 3, 3, 3, if I do this 3 plus and so on, then can I say this will be greater than or less than what? Tell me. Are you getting my point? See, I am asking that d1 is greater than equal to 3. d2 is greater than equal to 3. d3 is greater than equal to 3. And dk is greater than equal to 3. Every di is greater than equal to 3. Okay, every di that is greater than equal to 3. So tell me, if I do this k times, so that will be less than equal to, yes or no? Very simple point. See, this is very simple point because every di is greater than equal to 3. Okay, so if I do summation of all the degrees, that will be greater than equal to this value. So this is what I'm saying. So remember what I'm saying. I'm saying that this 3k, where k is the number of faces, this is less than equal to 2e. Yes or no? This is less than equal to 2e. This is less than equal to 2e. And what is this? This k. What is this k? This is the number of faces. This is the number of faces. And we can denote it by f. This is the number of faces. Okay, so very simple point. Very simple point. So remember, this 3 into f, this will be less than equal to this value. And remember, this value is equal to 2e. Okay, so finally I can say 3f, that is less than equal to 2e. Is this clear? Please tell me. Please tell me, did you understand this equation? How this equation we got? Did you understand this equation? See, very simple point. This we already know degree of all the summation of degree of all the faces. If I do summation of degree of all the faces, that will be 2e. Now you can easily see, let's assume you have k faces. These are your faces, f1, f2, f3, fk. These are the faces. Now let's assume these are the degrees. This face has degree d1, this face has degree d2, this face has degree dk. Now we already know that in any connected planar graph, if you have a connected planar graph with at least 3 vertices, then degree of every face will be at least 3. So you can see degree of this face will be at least 3, degree of this face will be at least 3, and so on. So you can easily notice, if I add all these di, that will be greater than equal to if I add this 3, 3, 3, 3. Okay, so very simple point. So finally, what equation I got? I got this equation that 3 into k, that is less than equal to total degree. 3 into k, that is less than equal to total degree of faces. Total degree of faces, that is 2e. Okay, so I can say 3 into k, that is less than equal to 2e. And this k is number of faces. So finally, I can say that 3 into f, that is less than equal to 2e. Okay, so we got this equation. Remember what we got? We got 3 into f, that is less than equal to 2e. Okay, that is less than equal to 2e. This equation we got. We got this equation. Now what we can do? Now you can apply the Euler theorem. See, this is your equation number 1. Now, what Euler formula says? Tell me. What Euler formula says? Let me know. V, number of vertices plus number of faces, that is equal to number of edges plus, because this is a connected graph. Because this is a connected graph, so C equal to 1, right? Yes or no? Euler formula for connected graph, because we are taking a connected graph. We are considering connected graph. You are considering connected graph. So this is your Euler formula. So from here you can notice f is less than equal to 2e by 3. Yes or no? Now you just look at these two equations. This is your equation number 2. This is your equation number 2. Now you just look at these two equations and tell me what you can derive. See, equation number 1 is saying that f is less than equal to 2e divided by 3. This is what you have. Okay, this is what you have from the equation number 1. This is from equation number 1. Okay, very simple. See, we are saying that v plus f, that is equal to e plus 2. This is one equation. This is your equation number 1. Okay, another equation is f is less than equal to 2e divided by 3. Okay, these are the two equations that you have. Yes or no? Now you tell me, instead of f, if I put 2e divided by 3, then what will happen? Tell me. See, can I say that v plus f, that will be less than equal to v plus 2e divided by 3? Yes or no? Okay, because f is less than equal to 2e divided by 3. F is less than equal to 2e divided by 3. So you can add v. On both sides, you can add v. On both sides, you can add v. Okay, on both sides, you can add v. So you will get v plus f, that is less than equal to v plus 2e by 3. Now this v plus f, this is equal to e by 2. This is, this is equal to e plus 2. That is less than equal to v plus 2e by 3. Now you multiply with 3. So what you will get? Tell me. If you multiply with 3, then you will get this is less than equal to 3v. Multiply with 3. What you will get? So finally, tell me, from here what you got? Let me know. From here what you got? So what you got here? You got e is less than equal to 3v minus 6. Yes or no? That's it. This is our result 1. Okay, this is your result number 1. Result number 1 proved. Is this clear? Please tell me, did you understand this? So this is your result number 1. Okay, I hope you understood. So remember, this is the conclusion. This is the conclusion. See, if you have a connected planar graph with at least 3 vertices, okay, whatever, remember, you can take any connected graph. You can take any connected planar graph. Any connected planar graph you take, any connected planar graph with at least 3 vertices. With at least 3 vertices, what will happen? In any connected planar graph with at least 3 vertices, what will happen? Tell me. What will happen? This will happen that number of edges, that will be less than equal to 3v minus 6. So this is very important. Okay, we will use it. We will use it. Result number 1. We are going to use this result. Okay, we are going to use this result. Result number 1. We are going to use it. So just remember this. Okay, we have already proved it. The proof we have seen. But this result we will use, and this result simply says that if you have a connected, this is important, that you must have a connected planar graph. Okay, you have a connected planar simple graph with at least 3 vertices. This will work for at least 3 vertices. Okay, then in this situation I can say number of edges will be less than equal to 3 number of vertices minus 6. This is your result number 1. Remember, this result is one way. This result is one way. Okay, this is a note. What is the note? It is one way only. Okay, this result is one way. This result is only one way. What that means? This result is one way only. What that means? Tell me what that means. It means that if you have a connected planar graph, then this will happen. If you have a connected planar graph, okay, remember, if you have a connected planar graph, then this will happen. Then this will happen. Okay, if you have a connected planar graph with the number of vertices at least 3, if you have this, then I can say what will happen. Then this will happen. Number of edges is less than equal to 3v minus 6. This will happen. But remember, if this happens, then that does not mean you have a planar graph. Okay, if this is true, that does not mean that you have a planar graph. But tell me, if this is false, then what you can say? If this is false, then what you can say? Tell me. If E is, I can say, if E is greater than 3v minus 6, if this happens, then what I can say? Tell me. See, very simple point. If you have a connected planar graph, okay, then definitely this will happen. If this does not happen in a connected graph, if this does not happen, see, in a connected graph, if this does not happen, notice, I'm saying, in a connected graph, if this does not happen, then it means that is not planar. Yes or no? Very simple. In a connected graph, if this equation is not true, means if E is greater than 3v minus 6, then it means this is not a planar graph. This is not a planar graph. Okay, this is not a planar graph. Very simple. So remember, this equation, this is one way only. Let me give you example. 2 examples I am going to give you. Okay, see, what about K33? This K33, this is not planar, right? This is not planar. We already know this K33 is not planar. But this K33 will satisfy this equation. This K33, you know, this is not planar. This is connected. We already know. This is connected, but this is not planar. Okay, but this will satisfy this equation, remember. This will satisfy. This graph satisfies. What it satisfies? It satisfies that number of edges is less than equal to 3v minus 6. What is the number of edges in K33? In K33, what is the number of edges? That is 9. Okay, yes or no? That is 9. And number of vertices, that is 6. So you can see this equation. You can see this equation is satisfied. 9 is less than equal to. 9 is less than equal to what? 9 is less than equal to 12. This is satisfied. Yes or no? Is this clear? Please tell me. Is this clear? Let me know. So remember, this graph is not planar, but this equation is satisfied. Okay, so remember this point. If this equation is satisfied, that does not mean it is planar. So remember this point. Okay, see, very important point, that if you have planar, if you have connected planar, then this equation will be satisfied. Okay, so this is important. These things, these small things are important. So remember, if you have connected planar, if you have a connected planar graph, if you have a connected planar simple graph, okay, with at least 3 vertices, if you have this graph, then definitely this equation will be satisfied. Then definitely this equation will be satisfied. Okay, but if this equation is satisfied, that does not imply that you have a connected planar graph. Okay, remember, in a connected graph, if this equation is satisfied, if this equation is satisfied, then you cannot say anything. Remember, in a connected graph, if this equation is satisfied, then you cannot say it is planar or not. Then it does not mean that you have planar. Okay, it does not mean you have planar. It does not mean you have non-planar. Basically, you cannot say anything. Basically, you cannot say anything. Okay, very simple. But if this equation is not satisfied, 3v minus 6, if this equation is not satisfied, then you can say it is not planar. Then you can say it is not a planar. Okay. For example, you can say, let's take example. What about K5? Tell me. My question is, prove that K5 is not planar. Prove that this graph K5, complete graph on 5 vertices, is not planar. Can you prove it? Can you prove it? Prove that this graph is not planar. This is what we need to prove. So tell me, how will you prove it? Prove that this graph is not planar. How will you prove it? See, very simple. For this K5, is this equation satisfied? See, this K5 is connected. You already know this is connected. You already know this is connected. Is this equation satisfied? What about this equation? E, what is the number of edges? In K5, what is the number of edges? That is 5C2, that is 10. Number of edges. This is a, remember K5, this is complete graph. This is your complete graph on 5 vertices. This is your complete graph on 5 vertices. Okay, so remember, number of edges will be 10. Okay. And what is the number of vertices? That is 5. So in this graph K5, you can see that E is not less than equal to 3v minus 6. Agree or not? Yes or no? Okay, you can check, because E is 10. Okay, E is 10. That is not less than equal to 9. Okay, that is not less than equal to 9. So you can see this K5 does not satisfy this equation. Is this clear? So you can see for K5, what will happen? Notice. For K5, what will happen? See, this K5 is connected. This K5 is connected. This graph K5, this is connected. But this equation is not satisfied. So what you can say? This equation is not satisfied. So what you can say? This graph is connected, but this equation is not satisfied. So what you can say? I can say this K5 is not planar. I can say this K5, this is not a planar. This is your proof. Hence proved. Yes or no? This is your proof. So I told you that we will see that K5 is not planar. We will see the proof. And this is your proof. Is this clear? Let me know. So very simple. Okay, so this result we have seen. Now let's see one more result. That is your result number 2. Okay, now let's see result number 2. See, before we see result number 2, you tell me one thing. How can you have degree 3 phase in a planar graph? If you want degree 3 phase, then what you must have in your graph? Tell me. A simple question I am asking. See, I am asking a very simple question, that if you have a degree 3 phase, then what you must have in your graph? Tell me. This is my question. A planar graph has degree 3 phase. Okay, if your planar graph has degree 3 phase, then what you must have? Then what you can say about this graph? A planar graph G has degree 3 phase, has a degree 3 phase. Then what you can say about G? Then what we can say about G? Tell me. Just think about it and tell me what we can say about G. Let me know. See, read this question. I am asking, a planar graph has some degree 3 phase. Okay, some degree 3 phase you have. You have some degree 3 phase. There is a phase with degree 3. Then what you can say about G? Definitely G contains at least one triangle. Yes or no? What you can say about G? Definitely G contains at least one triangle. Yes or no? G contains at least one triangle. At least one triangle. Yes, correct. There must be at least one triangle. Okay, G must contain at least one triangle. If you want degree 3 phase, see, if you want a degree 3 phase, just look at it. If you want degree 3 phase, then you must have a triangle. Now here you can notice, if you take this graph, then this is F1, this is F2. Here degree of F1 is also 3 and degree of F2 is also 3. Degree of F1, that is 3. Degree of F2, that is also 3. So remember, very simple point. If you want degree 3 face, you want to touch three edges. You want to touch 3 edges. You want to be surrounded by 3 edges. Degree 3 face means you are surrounded by 3 edges. Yes or no? Degree 3 face, what that means? Degree 3 face, that simply means surrounded by 3 edges. Yes, correct. Surrounded by 3 edges. Surrounded by 3 edges. Okay. And if you are surrounded by 3 edges, that simply means this is a triangle. This is a triangle. Okay. So very simple point. Now tell me, if you don't have any triangle, then what you can say? If you have a connected planar graph without any triangle, you have a connected planar graph. You have connected planar simple graph without any triangle. Now tell me what you can say. You have connected planar simple graph with at least 3 vertices, and without triangle, and without any triangle. There is no triangle in your graph. There is no triangle in your graph, and without triangle. Then what you can say? Please tell me. Then what we can say about degree of face? Then what we can say about degree of any face? Please tell me. A simple question I am asking. What you can say about degree of any face? If you have a connected planar graph with at least 3 vertices and without triangle, then degree of any face, that will be what? See, normally degree of, in this, what is the degree of any face? If I give you only this much, then what will be degree of any face? See, if I only give you this much, please notice, if I only give you this much, in this much, what is the degree of any face? If I only give you this much, then degree of any face will be greater than equal to 3. Yes or no? And if you have no triangle, that means degree 3 is not possible. Without triangle means degree 3 not possible. Degree of face cannot be 3. So finally, what is the answer? Are you getting my point? Without triangle means degree 3 face is not possible. Degree 3 face is not possible. And you have connected planar graph with at least 3 vertices. So degree of every face will be at least 3. But degree 3 face is not possible. So finally, I can say degree of any face will be greater than equal to 4. Yes or no? Degree of any face, that will be greater than equal to 4. So this is your result. Okay. See, if you have a connected planar graph with at least 3 vertices, then degree of every face will be at least 3. If there is no triangle, then degree of every face will be at least 4. If there is no triangle, then degree of every face will be at least 4. Now let's see our result. Number 2. The result number 2 is saying, in any connected simple planar graph without any triangle, this equation will be satisfied. Number of edges will be less than equal to 2v minus 4. 2v minus 4. And very easily you can prove this also. Let's see the proof. What is the proof? Tell me. You have a connected planar graph. Okay, remember, you have a connected simple planar graph. With at least 3 vertices. And no triangle. And there is no triangle in your graph. You have no triangle. Okay. This type of graph you have. There is no triangle. And what you want to prove? We want to prove that number of edges, that will be less than equal to 2v minus 4. This is what we want to prove. So can you prove it? Yes, you can easily prove. What is the proof? See, first of all, you tell me, in this type of graph, what is the degree of every face? In this type of graph, connected graph, at least 3 vertices and no triangle, what you can say about degree of any face? In this type of graph, you have a connected graph. Okay, see, you have a connected simple planar graph. Okay, with at least 3 vertices, and no triangle. And there is no triangle. For this type of graph, what you can say? I can say degree of any face will be at least 4. For this type of graph, you can say degree of any face, whatever face you take, degree of any face will be greater than equal to 4. Okay, that will be greater than equal to 4. So this is the first point. What the second point? You already know that total degree. You already know total degree will be what? Total degree of faces. Tell me, what will be total degree of faces? That will be twice the number of edges. That will be twice the number of edges. Yes or no? Now you tell me, this is minimum, right? See, this is minimum. Agree? This one, this 4, this is the minimum. I can say this is the minimum. So you tell me, if I take this minimum, means 4 into f, then that should be less than the actual value. Yes or no? If I take this minimum, this 4 is minimum. Okay, this 4 is minimum. This degree, this 4, degree of every face is minimum 4. Degree of every face, that is greater than equal to 4. So if I take this minimum, then that will be less than equal to the actual value. Yes or no? And this actual value, this is 2e. This actual value is 2e. So I can say 4f, that is less than equal to 2e. From here, I can say f is less than equal to e by 2. Okay, yes or no? So you got this, f is less than equal to e by 2. And what Euler says? What Euler formula says? Euler formula for connected graph. We have a connected graph, remember. What Euler formula says for connected graph? It says that v plus f, that is equal to e plus 2. Now you combine these two. F is less than equal to e by 2. And Euler formula says that v plus f is equal to e plus 2. Now you combine these two. So from here, I can add v. On both sides, I can add v. Okay, now you can see this value, this is actually equal to e plus 2. This value is equal to e plus 2. So I got what? I got e plus 2 is less than equal to v plus e by 2. So finally what I got? You can multiply with 2. So what you will get? Okay, so finally you will get e is less than equal to 2v minus 4. That's it. Yes or no? You got this. Is this clear? So very simple. This is your proof. Hence it. That's it. Okay, so we have seen this proof. So remember this result number 2. Is this clear? The result number 2, is this clear? The result number 2 is very simple. It says that if you have a connected planar graph, you have a connected simple planar graph, with at least 3 vertices and no 3 length cycle. Okay, and no 3 length cycle. Then what will happen? Tell me. For this type of graph, what will happen? Number of edges will be less than equal to 2v minus 4. This will happen. Okay. Is this clear? Very simple, right? Very simple. Now you tell me a simple point. If you have a bipartite graph, will this be applicable? See, I'm asking a consequence. See, in a bipartite graph, there is no odd length cycle. Yes or no? Okay, yes or no? In a bipartite graph, notice, observe. So make this observation. See, in a bipartite graph, if you have a bipartite graph, what will happen? Tell me. In a bipartite graph, there is no odd length cycle. So if there is no odd length cycle, in a bipartite graph, there is no odd length cycle. It means there is no triangle also. Yes or no? If there is no odd length cycle, that means there is no triangle also. Is this clear? So in a bipartite graph, there is no triangle. Yes or no? So very simple. So if you have a bipartite graph, this formula will be applicable. In a bipartite graph, you don't have triangle. If you have a bipartite graph, there is no triangle. So this is what I'm saying. If you have a connected bipartite graph, then this will be applicable. If you have a connected bipartite graph, okay, planar graph. If you have a bipartite connected planar graph, then what I can say, tell me? with at least 3 vertices. With at least 3 vertices. So very simple. I am saying if you have a connected bipartite planar graph with at least 3 vertices, then what I can say, tell me. Then I can say number of edges will be less than equal to 2v minus 4. Number of edges will be less than equal to 2v minus 4. Yes or no? Because bipartite means there is no triangle. Bipartite means there is no triangle. See this bipartite, this means no triangle. This means no odd length cycle. This means no odd length cycle. So there is no triangle. So there is no triangle, right? Yes or no? There is no odd length cycle. So there is no triangle. So if you have a connected bipartite planar graph, then this theorem will be applicable. Okay? Very simple, right? Yes or no? So these we have seen. So these two results we have seen. Let me give you a conclusion of both of them. These are one way. Okay? This is conclusion of both of them. I am telling you the conclusion. These two results are important, remember. Okay, we have seen the proof also. These are important. So remember what is the first result? First of all, we are considering only connected planar graph. Okay, we are considering only connected simple planar graph. So I will not write it again and again. We are considering connected simple planar graph with at least 3 vertices. With at least 3 vertices. This is what we are considering. We are considering connected simple planar graph with at least 3 vertices. Now, what are the results that we got? We got this result. The first result is, if you have this type of graph, connected planar graph with at least 3 vertices, then first result is E should be less than equal to 3v minus 6. This is the first result. What is the second result? What is the second result? If no triangle, then what will happen? Tell me. Then E will be less than equal to 2v minus 4. Okay, so these are the two results that we got. And these are one way only. These results are one way only. Remember. Okay, both results are only one way. Both results are only one way. Both results are only one way. So if these are satisfied, can I say that graph will be planar? If these are satisfied, can I say that graph will be planar? No. If these are not satisfied, then I can say the graph is not planar. Yes or no? Is this clear? Prove that K33 is not planar. My question is this. Prove that this graph K33 is not planar. Prove it. Can you prove it? This graph K33, this is not planar. Can you prove it? This graph K33. See this K33, this is bipartite, right? Notice. This K33. This K33, this is connected. You know this is connected. You know this is bipartite. You know this is bipartite. Bipartite means there is no triangle also. There is no triangle. Okay, bipartite simply means there is no triangle. Bipartite means there is no odd cycle. There is no odd length cycle. There is no odd length cycle. So there is no triangle also. So this is connected. This is bipartite. But still, is this equation satisfied? Tell me. What about this equation? Is this satisfied or not? See, number of edges. What is that? Number of edges. That is 9. Number of vertices is 6. Is this equation satisfied? Please tell me. Is this equation satisfied? So this equation is not satisfied, right? 9 is less than equal to 8. This equation is not satisfied. Agree? This equation is not satisfied. So what I can say? This equation is not satisfied. So what I can say? So I can say, so this K33 is not planar. Yes or no? So this K33 not planar. So this graph is not planar. I hope you understood. Please tell me. Did you understand this proof? Let me know. So remember what we have proven. We have proven that K5, also K33, these are not planar. We have proved it. Please tell me so far, did you understand everything? Let me know. Did you understand everything so far? So remember, we have proved that K5 and K33. We have proved that K5 and K33, these are not planar. This is what we have proved. Okay, remember this point. We have proved these are not planar. So remember this K5, this is connected graph. Notice. This is connected graph but this violates this equation. This violates this equation. E is less than equal to 3v minus 6. 3v minus 6. Okay. So that is the reason. This is connected, but it violates this equation. So from these two, what I can say? I can say K5 is not planar. K5 is not planar. Similarly, what about K33? What about K33? This K33. This is connected. This is connected. This is bipartite. Okay, bipartite means no triangle. Bipartite means no triangle. So this is connected and there is no triangle. But this violates. E is less than equal to 2v minus 4. So from these three, what I can say? From these three, what I can say? Tell me. From these three, I can say this K33 not planar. This graph K33, this is not planar. Okay, so very simple idea. I hope this is clear. So we have proved that K5, K33, these are not planar. These graphs are not planar. Means you cannot draw these graphs without edge crossing. These two graphs you cannot draw without edge crossing. Whatever you do, edge crossing will happen. So this is what we have proved. This K5, also this K33, these are not planar. Okay, we have proved it. So far, is everything clear? Please tell me. Let me know. See, we have seen two results. Very simple result. These are not complicated. Very simple result. And you can easily prove. Okay, the proof is also very simple. We have two simple results. Result 1, result 2. Two simple results we have. Using those simple results, we can prove that K5, also K33, these are not planar. Okay. So tell me, so far, did you understand everything? Let me know. Let me know so far, did you understand everything? Any doubt? Let me know. Is there any doubt so far? Now let's see this topic, that is four-color theorem. What this theorem says. Let's see what this theorem says. This theorem says that every planar graph is four-colorable. Okay. Every planar graph is four-colorable. What this means? Four-colorable. This means chromatic number. Chromatic number is less than equal to 4. Yes or no? Four-colorable. This means chromatic number is less than equal to 4. This means chromatic number is less than equal to 4. Is this clear? So what this theorem says? This theorem says that every planar graph has chromatic number less than equal to 4. Every planar graph, you can take any planar graph, you can take. Every planar graph has chromatic number less than equal to 4. Okay. Is this clear? Please tell me. This is called four-color theorem. This is very popular, let me tell you. Four-color theorem. Four-color theorem. The name itself is telling you. Four-color theorem. This means every planar graph. Okay, that is four-colorable. Means for every planar graph, the chromatic number is less than equal to 4. Okay. And let me tell you something interesting about this theorem. Something very interesting about this theorem. There is no person in this world, there is not a single person who has read its proof. See, that is interesting. What I'm saying, I'm saying in this world, there is not a single person who has read its proof. Then how is it a theorem? Can anyone tell me? Is it a theorem if no person has read its proof? Please tell me. Will you consider this as a theorem if there is no human has ever read the proof? Please tell me. See what I'm saying. See, I'm saying that this theorem we have, that every planar graph is four-colorable. Means every planar graph has chromatic number less than equal to 4. But what I'm saying this theorem, for this theorem, there is no human, I can say. There is no single person who has read the proof of this theorem. Then from where this proof came? So the answer is, this is the first theorem which was proven by computer. This is the first theorem. This is the first theorem that was proven by computer. This was proven by computer. Okay. And for a long time, let me tell you, This was proven by computer, and that is the reason many mathematicians, they did not accept this proof. Okay, what happened? Let me tell you. This four color theorem, this has an interesting history. This four color theorem, very interesting history is there. See, this was proven by computer. Okay, this was proven by computer. Using computer, it was proven. Now, because it was proven by computer, then naturally mathematicians did not accept this proof. Okay, many mathematicians, they did not accept this proof because this was proven by computer. Okay, so many mathematicians, they did not accept this proof. Then finally, what happened in 2005? In 2005, it was again proved by computer. Okay, it was again proved by computer in a different way. Okay, see, it was proved by computer. I can say in 1970s or something like that. Okay, it was proved by computer in 1970s or 1980s. Okay, so it was proved by computer at that point of time. Then in 2005, it was again proved by computer. Now slowly, mathematicians, they accepted this proof. Okay, are you getting my point? So this is very interesting that it was proven by computer. Remember, there is no human, there is not a single person who has read the proof. It was proven by computer. You can read this four color theorem. This is very interesting theorem. This says that the chromatic number of any planar graph, that is at most 4. Read this. The chromatic number of any planar graph, that is at most 4. And this was the first theorem which was proven by computer. It was the first theorem to be proved by computer. This proof was not accepted by many mathematicians. But slowly, the proof has been accepted. You can see, slowly, the proof has been accepted. But still, there are some mathematicians who do not accept the proof. Still, you can see, some doubters are there. Still, there are some mathematicians who do not accept this proof. Okay, but anyway, this is a very simple point, that the chromatic number of any planar graph, that is at most 4. If you have a planar graph, then the chromatic number is at most 4. And this four color theorem is very interesting. This is very popular, let me tell you, because this is the first theorem to be proven by computer. Let me tell you one more thing. Even today, there is no proof without computer. Even today. Okay. Is this clear? Even today, remember, there is no proof without computer. So if you want to gain popularity, okay, if you want to become, I can say, very popular in this world, then you can try to prove it without computer. Okay, basically without computer, can you try to prove it? Just try to prove it without computer. You will become very popular. Okay, because for this theorem, there is no proof available without computer. Without computer, there is no proof available. So anyway, this is your four color theorem. I hope you understood. So that's it. This is your chapter. So we have seen everything. We have seen what is a planar graph. A graph is planar if you can draw this without edge crossing. We have seen Euler formula. We have seen for connected graph, what is the Euler formula. We have seen K5, K33, these are not planar. We have seen the proof also. And we have seen four color theorem. Chromatic number of any planar graph is at most 4. This is your planar graph. We have seen everything. Anyone has any doubt, let me know. Please tell me, did you understand everything? Let me know. Did you understand everything in this planar graph? Everything that we have seen every statement, every theorem, every result with proof we have seen. So please tell me, did you understand this planar graph and did you enjoy? Did you find this very interesting, this topic, this planar graph? This is very interesting topic. Okay, all the proof are very interesting. If you notice, we have seen the proof of Euler formula. That is also very interesting. Okay, a beautiful proof of Euler formula. And we have seen some important results. The proof also we have seen, and some questions we have done, and we have seen four color theorem. So everything in this planar graph we have seen. Okay, anyone has any doubt, let me know. Anyone has any doubt, please tell me. Any doubt, anyone? Okay, thank you everyone. So this is your planar graph. We have seen everything. Okay, thank you.